Hi, everybody. We're here today to do a deep dive on the SPL Machine Head. That was an original hardware piece, fully digital hardware processor that we created in the mid-90s, 97, so to speak, was the year. Today, we're going to talk about how we created our plugin out of the code that was designed back in the days. That code needed to be revised to be updated for today. And so we needed to be involved with the original company that created that code. So we were now really pleased to have Lukas from SoundArt here with us. He and his partner Frank Hartmann, they both own the company SoundArt, and they were the guys who created, in my opinion, it was actually the very first tape saturation processor in the digital world, which we then had running in our SPL Machine Head back in the days. So sit back and relax. It's going to be a long, deep dive, but when we're done with that, you know everything you need to know about the SPL Machine Head. Have fun. Kai, thanks for having you. Great you have found the time to come here all the way down from Hamburg. You started earlier thinking about this project of tape saturation than I did. To me, it was 96, 97-ish when we first got to know about your algorithm. But just tell us, how did you start with this project? What spiked the interest to go digital tape saturation?
So actually the creative cell of all this was the recording studio Jam Productions that I had in the 90s. And in that studio we developed, we had different tape machines. Started with 8-track, then there was 16-track. In that case, it was a Fostex E16 with Dolby C, so it's half inch, so very limited. And then we upgraded to a 2-inch 24-track machine. It was a Lyrac 533.
The TR, yeah.
Yeah,
I remember that one. Yeah.
So from Denmark, when we got that, we got more or less blown away by the good things that this kind of machine did to the music we produced on it. And actually looking at that, I think it was in the row of the machines that we had. The first machine, really, we could use the high levels, the magnetic effects that are happening when you overdrive a tape machine. And we thought, on the other hand, we have been starting also hard disk recording. So we wanted to have that also in the digital domain. So that was the idea, to want to have something like that. We searched for that and it was not available. So we said, okay, we are both engineers, also engineers for communication engineering. So we have a bit of software background also. And we said, okay, we do it on our own. And in addition to that, we thought, okay, it would be very nice if we have a digital implementation that is not limited to some parameter connections that analog tape machine has. So if you drive an analog tape machine really hot, you get this kind of fatness and stuff like that, but you lose high frequency content.
Yeah, right.
And we said it would be really great to have the saturation effect, but without the loss of high frequency, or with a feature that the user can decide, do I want to have a reduction of high
frequency? Yeah.
So, and the same is actually true for head mirror resonance. So in the normal setup, the aim of the tape machine is to make it as flat as possible in the low frequency area. And we also wanted to bring this compensation also to the user, that the user can say, okay, I like the the additional punch from the head mirror resonance, and I can select how much of it do I want and how much compensation do I want. So that's more or less why we started that and what our objective was.
Similar thing is also with the high tape speed, right? That you have a certain loss of low frequencies when you switch to 30 IPS.
Yes.
And but that is for everybody. That is sort of an unwanted effect on a tape machine. And you just said, "Oh well, we don't do that. We don't replicate that less low frequency part."
That was more or less in the practical production. I often used 19 and not
50,
15 and not 30,
30.
because I said, okay, I take a little worse signal to noise, but the full bass.
Yeah, I think we're going to be mixed up with centimeters per second versus 2
Yes.
inch per second, right? So
Okay.
the 19
Sorry
was
for
the
that.
7. It's fine, but the 19 was centimeters was like the 7.5 inch per second, if I recall correctly,
Yes.
and that was the lowest possible speed, but it has the fattest bass response. So I wonder, I have the idea to create a digital representation of an analog tape machine behavior. Now, how do you start with such a project?
So the first thing is to do your homework, which means looking at the analog tape machine and identifying the different circuit blocks this analog machine is made of.
So you go through the service manuals, you take a look at all of the schematics and the filter blocks, the emphasis filters and whatsoever, understanding what the machine actually,
How it is structured.
how is the signal flow in the machine, how is it structured? Okay, I get that.
And so we have can identify some different parts we can look at separately, but the most interesting part is the non-linear behavior of the machine. So and to get an idea about that, we made a lot of measurements actually, finding out about the characteristic curve of the nonlinear behavior of the machine. So for different frequencies, we measured this curve, and we got an idea what is going on there. So, and with all these measurements, still first in the analog domain, then we go to a tool that is called MATLAB. It's more than a tool. It's just an environment where you can mathematically do things.
Okay.
So, and these measurements we use then to evaluate and to plot graphs from this curves, and then we just print it out. We did a lot of measurements, printed it all out, and just put it on the floor somewhere on the studio floor. It was all full, and then we looked at that, and then there's some kind of creative process beginning. Just saying, clustering these measurements and seeing some things that are put together. Which axis maybe could be used, and then there's the first hypothesis. Okay, what kind of system or what kind of structure we can use for modeling that, and then we take the measurements as parameters for the model and calculate the model. So we also have graphical representations how close this is to the analog one. Yeah, and then if it looks successful in the end, then we also do a listening test, like processing where we have processed audio from the analog machine, and also we calculate the processing on the same audio. So this is at that point of time, it's offline. There's nothing real time or something like that. It's just for finding the direction or the structure of the algorithm. And there were several tries or several structures tried out. I think actually I've been looking in our old documentation yesterday evening just to find out what we did there. And it was, I think we had about I would say 5 to 6 different different hypotheses, and then in the end, we found a solution which is actually a little bit surprising how it was, and also
In what respect? Surprising.
surprising about the harmonic content that is used to really to model that saturation.
Is there a time signature also relevant in that, not just like a static
It is.
characteristic?
That was first step, the static. So
Yeah.
we have the static measurements, we have the transfer curve, and this kind of stuff, and then we had to look at the dynamic behavior of the animal, and for that we created some special test signals that are aiming at somehow triggering this kind of fast changes in the time behavior. And with that,
What kind of test signals are those?
some signals that are fast changing in amplitude and stopping and beginning, and
But like sine waves, tones, or individual tones, or burst signals, or what?
more or less tones of different frequencies.
All right.
And then you can of higher frequencies, more or less, and then you can in a good case see what happens there. So we get the modeling of the time behavior, and in this case there is a time behavior, and this is especially complex because there is, in the magnetization process, there's something that is called hysteresis, which is a nonlinear behavior of all the small magnetic pieces on the tape. And they have, when they get magnetized, they have some kind of threshold when they start to get magnetized. And then when they stop to be magnetized, there's a different level when they stop. So you have a very complex thing that it is relevant what has happened before to have the to have the right threshold on there. So it's very complex. We measured that as a black box, but that means because the physics is so complex, you can expect that there is some time behavior in there, and that also had to be modeled.
Yeah. Now tell me. I mean, the tools that you've been using at the time back in the 90s. What were they? I mean, you talked about MATLAB as a simulation environment, so to speak, where you could actually model things. But I also know that you started to work on your own filter banks, filter designs,
Yeah.
and that because there were limitations in what you could find, so you need to create them on your own to really have a full representation of what's happening. Can you tell us a bit more about designing those filters and the limitations back in the days?
The case is that the design algorithms that are available for digital filters are not very suitable to create good sounding audio filters.
Okay.
And they also have some numerical limitations. That means, so if you have very strict ideas how your filter should be, or many different ideas what the filter should fulfill, then you relatively soon reach the border of the numeric calculation that is, I would say, that produces a meaningful output. And this is why we were using, or this is one of the reasons why we were using a specific special environment which allows us to calculate with infinite resolution, this kind of stuff. Infinite means, well, you trade in time in that. So it means, so we did most of these calculations with 4096 bits. resolution, which is required because these numerics are so critical, and you go to the borders of whatever. You derive in the end coefficients which are, well, they can be used, but all the calculation in between reaches borders, very very low numbers and stuff like that. So we have, or Frank more or less had put in place this environment where we could do these calculations, which meant, on the other hand, okay, if we want to have the design result in the 90s, it can mean just look at it tomorrow. But it's not today. We also use that for the filters in the new plugin. Then it was a question of some seconds, so it's not.
Back in the days, it was an overnight job.
Yeah. So, but it made it possible to approximate these filters in a meaningful way. So that was.
So let me get this straight. You've been graphically getting close with the algorithm that you create to what the analog measurements told you. That was the first step. Then in the second step, you sort of listen to what you have and you realized, hey, those filters doesn't really sound like good audio. So you started to create your own set of filter designs and filter banks to actually derive coefficients that do sound musical and represent what the tape machine really does.
That's correct. And also, we need this very precise environment for one other thing. So actually, if you are having a digital filter, this filter is implemented in a structure, which is like an equation or so. And depending on how this is expressed, so you can express the same filter in a different kind of structure. And these structures actually have all different behavior concerning noise and concerning quantization noise. And you can shape these noise, or or let's say you can shape the way that the noise is depending on the parameters on the filters, for example. So like is saying, okay, if you take the standard approach, then the smaller the filter band is, the higher the noise is. But that must not be the case. So there are different approaches. And now coming back to this precision environment, if you want to research on different structures, you need a very, very high precision reference. Otherwise, you cannot say, okay, what is the noise and what not. So, and that was the other part we needed this environment for, or this tool, to compare different filter structures and find the structure that we take. Actually, the interesting fact about that is that all the theory about these structures, this is very old. In the 50s or so, some mathematics found these kind of stuff. And they wrote in their papers it will never be realized because it's so it takes so much performance. There will never be computers that can do that. But as you see, even in the 90s there were. But all these old papers were not easy to find.
So you like researched in libraries and stuff like that? Yeah. Okay.
That was. And we have found different ones and compared them, and then.
Oh shit! So you actually went so deep that you started to compare the very basic filter models that will ever be described mathematically to see if they're applying those would create more realistic results for
more for quantization noise.
For quantization noises.
That's,
all right.
And I think that's also maybe a difference between different equalizers, digital equalizers that are out there at the moment. I don't know, but that was why we went in that direction. So that was more of a side finding for the machine head then.
So tell me, now, last year we've been discussing, or we sort of like came back together in a way on the telephone. Actually, you called me up and say, hey, Wouldn't it be nice? And I said, yeah, we were thinking along the same path. It would be nice to get the machine head back to life. And uh, we were all really excited to go that road. But I knew that we're looking at data that was like, or machines that were like 30 years old. And I remember you were saying, "Oh, I have to do some archaeology on
Yes.
some and on this. Tell me about that because that's, I mean, there was luck involved to really get this project started. But
Well,
yeah,
but it was luck, but actually a bit of statistics also,
all right,
because yeah, we had to find well, the old backups of the source code that we had, and yeah, even found actually a working development environment on an old laptop from that days. It was still bootable, but actually it is not possible to communicate with this laptop because that was the time when we had this old Windows, which is not there's no network card. There is a network card in the system, and on the physical level they communicate. But we were
the protocol is different.
we were never able to access to the network in any way. But we had all this backup CDs, and the backup CDs were readable, and so we had on the one hand the source code. We needed on the other hand the machine on which the old reference implementation on a workstation was running, so that we could somehow compare. I come back in a minute to how why this is important. So we have also the task. We had the task to bring this old Windows 2000 workstation with Pentium Pro processor that big like a shoe sole. So yeah, it's also booted, and the boot password was found. So we had this old workstation working for reference. We also had an old machine head hardware. Okay, so also to this workstation there was no access possible. It was before USB and all this kind of stuff. So it's not all the things. Forget about that. But there was a digital audio card in there with SPDIF. So we could use this workstation more or less as a black box, SPDIF in, SPDIF out, and so we had the reference also available. We had this guy here, yeah, and then we have the old source code, and then it was quite a time jump for the source code from the first microvisual C++ version to version 19, which is at the moment the one. Yeah, and the good thing is we could compile this source code. So there was a starting point.
Did you understood what you did back then? I mean, did you recall all of that, what had happened back in the days, or was there a learning curve for you involved as well?
Actually, not so much, because we did documentation at that time. So there exist also conceptual drawings and measurement screenshots and stuff from that time. So it was not meant to be looked at after 25 years. And looking at the source code you did 25 years ago is also, but that was relatively easy. And the very good thing is, on the very core, we didn't have to change anything, because I say this is this kind of dynamic time simulation part, which is the most complicated one. Yeah, that was fortunately working.
Right.
So we could compare that, and also we had to make sure that we really got the right version, because at that time there was no version management. So it was as it was. Auf Deutsch würde man sagen, wir hatten ja nichts.
We didn't add anything.
Yeah. So, but Frank, who is the one of us who did all the time C++ development, then took the code and modernized it to the recent C++ standards. But all the time there was some kind of quality control that the output, the audio output, stays the same. So and then we really had to make sure that the output from the newly compiled plugin does exactly the same as the plugin on the workstation, and that was reached.
Okay, but tell me, I remember when we did the platform back in the days, where we had the loudness maximizer and the spectralizer. Oh, by the way, folks, this is an interesting fact because he just told me that yesterday, and I really didn't know about this. Your thesis and for your diploma was the spectralizer.
Yeah, that's correct.
So I didn't know. So you did know a lot about harmonical behavior just because of that, and you probably could use some of that for the creation of the tape machine.
Absolutely, and also about how this sounds.
Yeah.
And if you have so much research on harmonics, then at least if you are an audio engineer, you know how it sounds and what the characteristics of the different harmonics is, and what is preferable and what maybe not.
So just so you know, we had three processors. The first one we did was actually the spectralizer, and that was a digital exciter, so to speak. And you could dial in even an odd harmonics separately and mix them at separate level. And it really sounded cool for a digital filter. I mean, that was the thing. It was really hard to create good sounding digital filters at the time, especially in the realm of harmonics. The second product that we made was the loudness maximizer. Well, and that was part of the whole loudness war that came out of it. I apologize for that. Yeah, luckily these days are over and is putting too much emphasis on increased loudness anymore. I'm happy for that. So we had to create a platform at that time, and for us, I mean, we were an analog company, and it was really intriguing to do something in the digital world because that was exploding in the 90s. The workstation came along, Pro Tools was there since 92, and everything seems to go into the box, or at least there wasn't enough processing power. So really intense processing had to be outside of the box. That's why Pro Tools was successful. And we needed to develop a digital processing platform. Honestly, we didn't know how. So I teamed, first of all, I needed to find a company that does that. And I found a company, I think it was Harald Obenland from Octum Design, who actually was the guy who designed the processing card in there. And it had two Motorola 5600 O2s on it, or three. No, yeah, it could have three, but we only stuffed two. Yeah, it was expandable to three of them. But it is extremely expensive to do this. So we got funding, and I applied for funding, and the Steinbeis Transferzentrum in Heilbronn, they actually were the company who put everything together, who gave us the funding that Octum could develop that platform. We, on the other hand, we designed the back, so the inputs and outputs, all of that, the power supply, the front panel, and we took care about all of the pieces to make this actually happen. And you provided the code that ran on the Motorola's. So, but they were like 24-bit fixed point, and now you were like in the world of floating point.
Yes.
And now there were limitations. Tell us about it to make this work on integer processing.
We had implemented the reference floating point version on the workstation. And you have to, if you go to fixed point processing, you have got to take care of a proper scaling. So that means moving all the gain structure in a way that more or less you do that by bit shifting. more or less, or in a way that there's no digital over taking place, no values greater than 1. So you even lose of the 24 bits. You lose several bits for scaling. So so it really gets narrow then to have clean 16-bit files. But what was our role in that? We did the reference implementation, and the code on the Motorola was implemented in an assembler, so machine code. And we had defined some test signal, which is actually a music signal, which is set up in a way that all the different processing states of the algorithm are really touched.
Okay.
And this test signal was processed once by the hardware unit, by the Motorola's, and once processed by the workstation. And then there was the difference was calculated. And this difference, the quality criteria was that the difference between these two is sufficient.
All right. So there is a diminishing of quality, actually.
I did the exercise again now because
Yeah.
I also had to know if we are in the right direction and stuff. So we are, I think what I would say, we are 88 dBs okay, which is much, I think, in that area. So, but we are between the workstation and the new plugin, we are a bit identical. But with what we didn't reach the 96, but the 88 to the fixed point, which is more than okay for the scenario, for the less bits that you have there. So
right. So after all these decades, digital audio evolved, and especially sample rates went up from 44.1, 48, which was the only sample rate that the hardware machine head could do. We go on to 96 and to 192, and now we're at 384 for the plugin. Even 768 is possible, but we don't do that on the plugin. But I remember you at one point last year when you were like working on this, you told me how difficult it actually became to get, especially the high frequency filter, to operate on higher sample rates than the 44.1 for 48 kilohertz.
yeah, that's true. We had in the original version, we had to redesign all these filters in a way that they are more or less the same as the original, but with higher sampling frequency. And you have, besides the performance problem, because you need longer filters, you have the situation when you want to do digital filters, and the corner frequency of that filters is very much lower than the Nyquist frequency, which is the half sampling frequency. Then you have two things happening. One thing is the design numerics are also running into that area what I explained before. It gets very critical. So with low numbers during the design of the filter, so we also needed our high precision environment. And also the filter gets very long, so you need more performance. And you have, with the new sampling frequency, you have to approximate the filter again. So we had to approximate a lot of filters because we have now a lot of sampling frequency. And before last year, we did that, as I described, a creative approach. Like, well, there were not so many coefficients, and then there was some kind of magic when tuning this, and until something reasonable comes out. But this creative approach was just not feasible for this amount of filters we had to create. And so this made actually Frank to invent approximation method which is more mathematical to put in like the old filter, the frequency response of the old filters that we have, and then design new filters for the higher sampling frequency. So that's also some actually in our company it's now called the shower process, because the idea was created while showering. How to do that? It's a mathematical idea which was then fine-tuned, and so on. We have now this approximation method, and then we managed it, but it was quite at the borders of numerical processing to design that, and that also helped us then to design all the other filters for the version we talk later about.
You also, when we talked about this last year, you were saying, and now we have all these add-ons. We can improve on the high frequency filter with the new technologies that you develop for that. We have the higher sample rate, and then you came out with we can also do the head mirror resonance, which was a parameter that we didn't have in the original machine head, but you created it back in the days already. And I said, oh yeah, wow, a new feature. Oh, that'll be awesome. I was just like on fire. And I was thinking, how do we do this then? And then I was talking to the guys who actually were involved in creating a plugin, which we at that time in the mid 2024 last year, we sort of put together the team that actually was there to create the whole plugin. And a big shout out to Gary Grutzek. He is the guy who actually wrote all the plugin, or he made the plugin with the algorithm that you provided. So he did a tremendous job on that. And so I asked him, could we actually do like two versions, like have one plugin with like two different algorithms behind them, and you can switch them in the plugin, because that would allow us then to have like an original version, and we didn't know the name at the time, so we called it the modern version or whatever, until we came out with Ultimate, because that was actually the ultimate thing, and the new feature was just really cool to have. And the head mirror resonance, because it was the opposite to what the high frequency was doing. We had something on the bottom end to manipulate as well for artistic reason. That might be sonically very, very useful. So I was up for that. And he said, yeah, I could do that. And another big shout out to Gary Litzak. He actually made the GUI design for us. Goran, sorry, did I say Gary Litzak?
Yeah. No.
Excuse me for that. Goran Litzak. And Goran, you're a true artist, I have to say. You're an artist on that. So we created the original machine head with a front panel that was actually
I like the fat around the potentiometers very much. The fat on the front plate.
Yeah, it was. He had like grease textures for like the around the pots, and he showed me what he was working on Photoshop with that, and he said he had like 5 or 6 layers of grease. And we said, do you like it a little bit more, a little bit less? Oh, I like this one, so we go for that. Then he also had dust in the LCD display, and he took pictures of the original ones where the dust was in there, but he had like another 6 layers of dust elements for the within the LCD display. And it was just so in detail. He was so in love with all of that, and I totally admire him for that. We also had like the front panel on the original one. I remember back in the days, we really had difficulties anodizing red. And it wasn't around a lot to do that. And we had to swap companies and in that process. And one company that delivered front panels to us, they looked like the original red back in when we got them, but they were not ultraviolet resistant enough. So over the time, they sort of like bleached out by and many of the machine heads have this bleached red, and we love that. We want to keep that. So he took photos of that. So the original really had that bleached front panel, and it has the marks on the 19-inch rack ears, and everything is in there. So from an original unit that we photographed, that we used for many, many, many years, and then we said, okay, let's do a second UI for the ultimate version, and that should be the real red. There's no dust, no grease. That's the fresh thing, and it's also got the new SPL logo on. So basically, we got two versions now. Going back to what is different there, and
I would say what is important to express, the original is really the original.
yeah,
So we have not changed things there. So we have even found one error with one coefficient within the implementation, the old implementation. There was one small error, not totally misleading, but an error. And it took me some sleepless night not to correct this error.
I remember.
To have really the original as original, even if we have some newer ideas now.
Yeah, you were struggling with that. I remember you called me up the one day and say, "Ah, this is a coefficient that is wrong, and we need to change that." And I went like, "No, no, nobody knows that, and it is part of the original sound. So no, we cannot change this." But that also brought up the idea of the ultimate version.
Yeah.
We can do this better now. We can do this more refined. And when I heard the first listening results on the ultimate version, I was just like really impressed. The refinement, the depth, the clarity. I mean, you switch the same setting between original and ultimate, you were like, whoa, the ultimate is just like so smooth, nice, open, clean. It's really like it's like, yeah, the original version was a rock and roll version.
Yes.
And it does that, and it's great for that. But if you go for mastering and you want to use it in more delicate and more refined applications, the ultimate version is just killer.
Actually, there are also applications for the original version, like that on if you are processing loops or guitars or so.
Yep.
So this is why we have the two versions. And yeah, what happened in between? So now we have about 100 to 1,000 times the performance possibilities that we had in 96. So there's a lot of more stuff that we can do. And we can, well, we have developed a lot better filter banks. They are longer because we have the performance. We can use the longer filters, which we couldn't before that. And also in the design of the filters, we could design them more precise and also better sounding. So that's one of the things which really gives a lot. We have less artifacts and all that. And on the other hand, and that's coming back to the head resonance filter. In the meantime, we have also developed other things and also some equalizer plugins. And with that, we developed a new filter structure for more analog-like filters. So these structures, which are infinite impulse response filters, so they are a complete different setup, which is useful for some other things if you want to have a more analog-like representation.
Mm-hmm.
And we use these new filters for the head resonance filter and also for the high frequency filter in the ultimate version. So because we think that for these two filters, only for these two, this is has the better result. So not for the other filters, not. So because all the decisions we do with the ears. So
Yeah.
for the core algorithm, we did not change that. But the filters itself were much longer and have much better features.
Right.
So yeah, and I'm also very happy so that we can prove what is possible now.
So with all the new filters that you designed, we now also we spoke about that, so that we also said, okay, let's make a finer resolution on it. The original version has a high pass filter where we had a range from -6 to +6, and it was just yeah, integer steps. So and we kept it that way for the original, but for the ultimate version, we figured a finer resolution would just be really nice, because it sounds so nice that you sort of like, oh, that's a bit too much, oh, that's not enough of that. So you sort of jump in between, and yeah, we then decided, let's make this like by 10th steps, so in between, so multiply the resolution by 10. So we did the same thing for the low frequency filter, and I believe we also changed the resolution of the drive. This one had like, the original had 0.2 dB steps, which we also changed to 0.1 dB steps in the ultimate version. Yeah. Thanks a lot. That was a very cool talk. I really enjoyed it. Thanks for being with us, Guy. And
Thanks also, it was very nice.
so, folks, that's the whole story. If you dig it, if you like it, if you want to dig deeper into it and even play with it, go to pluginalliance.com. You can download the test versions there and just listen to it and enjoy the original SPL Machine Head plugin. Bye bye.